Welcome everybody to lecture number 17, databases number 2. Today we're going to be talking about document databases, graph databases, and we'll be going over some examples. Full transparency, databases is one of our newer content for this semester, and frankly, it probably doesn't fit in 2 lectures in that it doesn't take up 2 lectures. So we may finish early again, unfortunately, but I have some extra time near the end just to kind of talk about, I guess, life or go over kind of more specific examples of deploying apps into the wild. So, if you have anything you want to learn about that's maybe web dev related, this is our last web dev lecture. We've gone over front end, we've gone over back end, now we're finishing up databases. From here on, we'll be moving on to topics, miscellaneous things like getting an internship, ML, as well as, the majority of the remainder of the class, which is going to be Rust and learning the Rust language. So if you do have anything you want to ask about web dev, the end of this lecture is really the time to mention it. If you're watching this recorded and you want to learn something about web dev, I guess shoot me a message or something, and I can even record like a little add-on just for people who are interested. In any case, let's go ahead and get started. So, if we remember last lecture, we talked about relational databases being, mainly SQL tables or SQL databases. These are the things that kind of look like Excel columns and Excel tables. So they have rows and columns, each column being a feature, each row being a sample, a entry into your database. Just a quick reminder, that first row is what we call the primary key usually, if it is unique. If it's not unique, then multiple columns can take up the primary key, just whatever you need to turn it to become unique, essentially, right? So let's talk now about document databases. So document databases are also referred to as object-oriented or NoSQL databases. Technically, if you remember from yesterday, NoSQL just refers to the language, structured query language. So technically, NoSQL is any language or any database that doesn't use the structured query language format and uses maybe a different format. That being said, these are usually document databases that are NoSQL. And in practice, most people just refer to document databases as NoSQL databases or object-oriented databases or object databases or whatnot. The terminology here is not necessarily clear. It's not necessarily clean cut. A lot of people just kind of call it whatever. Data is stored and queried as very often Json objects. So hopefully in your last homework, you may have gotten a little bit of familiarity with Json objects, mostly, just understanding that they are dictionaries, fancy dictionaries in Python. This allows us to interact with these objects in our database in a way that's much closer to how we interact with objects in code. So obviously in Python, you have objects that we're working with, classes, instantiations of classes, and these classes have attributes. Well, that's kind of the natural layout of JSON objects as well, or any dictionary for that matter, is you have the main dictionary, and it will have different attributes based on, the properties that it has, and these attributes can be varying in size. For example, one thing that can be relatively hard to do in SQL tables is an array that you don't know the size of, right? And that's very easy to do in kind of document databases. Of course, it's not impossible in either, and it's such kind of common practice that it's widely done in SQL tables as well. But it is maybe a little bit more work. Document databases allow us to have what we call flexible data schemas, a schema being how we're laying out our data. And again, this is a good thing and a bad thing, right? It's a good thing because we can have wonderful things like different size lists, and then it's maybe not such a good thing because if you allow your database to be more flexible, you can also run into more exceptions. So maybe you expect something to be in a certain format, it's not, and now you have to build out code to kind of handle that error. Most of our discussion in document databases is going to be revolving around MongoDB. MongoDB is by no means, the only NoSQL database. In fact, I would argue, probably hundreds. I have no idea how many there are. But MongoDB is a very popular one. And, a little bit of a fun fact, I used to, when I lived in Palo Alto for a summer, used to shop at a Whole Foods that was a block away from the MongoDB, I guess, headquarters there. And so I got to see their office a lot, and I talked to someone who worked there. And so now I'm a corporate shill for MongoDB, is basically the moral of that story. So how do we install MongoDB? Well, step one is you actually need to install the MongoDB server. And, of course, it hopefully should not be too surprising to everyone that you need to run a database on a separate server. The reason for this is because it has to deal with these requests very asynchronously, right? You may have many, many, many servers that are attempting to get or set information in the database server. And so you really kind of have to host it on a different instance so that you can handle that asynchronicity. Additionally, if this goes back to the idea of if you turn your server off, you don't want to lose all of your database information. MongoDB is very friendly in that they give us a free kind of cloud service to host these databases called Mongodb Atlas. I'll actually pull it up very quickly. So we can see here that it allows us to kind of host a database for free. And in fact, we'll open up a link that we're going to be working with a little bit later. And we can see that, they kind of give you a, granted, not very powerful computer, but a computer that allows you to host a database for free and host a database website for free. It gives you all sorts of fun statistics, how big your database is, how many operations you're doing, things like this. And so that's a little bit handy, just a little fun fact there. Anywho, so MongoDB Atlas is kind of what we can host that database on. And then when we're actually interacting with our database, we'll just do it in Python because we like Python. Python is easy. And to do that, we'll just pip install PyMongo. Py being Python, Mongo being MongoDB. Shouldn't be too surprising, I hope. So, let's talk about kind of the major steps. And if you remember, we talked about all of these in relational databases too. Create database, create table, setting instances in that table. Now, we are being kind of introduced to some new terms here, collections and documents, but don't worry, we'll talk about those very briefly. So step one, importing the module. Nothing crazy here. Just import PyMongo, right? Make sure it's pip installed, and so you won't get an error there. But hopefully that isn't too surprising. Next, we'll connect to the server, and so this big URL is something that's kind of provided by that online website. And then what we do is we create a client to connect to the other server. This part here is my password. I blocked it out because I don't want you all to know the password that I use for this. I hope that should be obvious. Next, we'll create a database in the server. And so the way you do this is we say client.database name, and we'll call that, our database object essentially. This is basically the same as saying create database in SQL. That's the headphones stay on sound. The next thing we'll do is create a collection. And so inside of our database, we have in relational databases, we have tables. In object-oriented databases, we have this thing called collections. Collections are like tables, but they are essentially lists of many, many documents. So while tables are, a list of many, many rows, collections are lists of many documents. And documents are kind of the core object, for lack of a better term, that we work with in object-oriented databases, and it represents kind of a single JSON object inside of our database. I made the sound myself, so I hope I didn't make it sound like the airplane seatbelt sound, but maybe it does. So again, a document represents kind of a single JSON object. Documents in a collection don't have to be the same schema. They can be different, but they probably should be the same schema for many, many reasons. The most important of which is if you try to query something and you're expecting a certain schema and you get a different schema, you're probably going to have a not so good time. Sorry about that. All documents should have a ID, or all documents are assigned an ID attribute. This is something internal. You don't have to set this. It is unique and it is indexed upon. And so when we create an item in our database, it automatically assigns that ID attribute. And so let's look a little bit at our code here. So we have, whoopsies. Okay, so again, we create our database, create our collection, and then create or insert our new object. And you can see if this would stop getting in the way, I don't know how to make that not get in the way. This is so sad. I'll wait for it to go away. We can see collection.insert1, and the parameter to that is a dictionary, right? Hopefully that shouldn't be too surprising, and that dictionary then gets converted into what we want it to be inside of our database, which is an object, a JSON object. So let's experiment a little bit with tying together Python classes and documents. And so hopefully you all are familiar with the new user.py file from your homework recently. We'll make a small adjustment to it. And so instead of phone number, we'll say page visits. And we'll have this toDict function that turns it into a dictionary. I forgot to, oh yeah, we can see page visits here. I did update it. So once again, we connect to our server. We create our database and we create our collection. And then we're going to create two new users. This is all, kind of still classic Python class, Eustis, Woostis, my email, and then the amount of times I visited this website, which, we're saying I'm a new user, so it'll start at 0. Same thing with Matt. And then we'll use this, once again, collection.insert1, convert me to a dictionary, and then we'll get the inserted ID, which just gives me the ID of me. The ID of the ID of the document that we had just inserted. Excuse me. And so we've learned about kind of our first function, which is .insert1, right? And you pass in a dictionary into this, and it adds it to your dictionary, or it adds it to your database. And in fact, we can load the database on the website, and we can see these objects in here. And so we see, Eustis, Woostis, 0 page visits in my email. Additionally, we see this ID attribute, which is, unique randomly generated string. And then I think each time it increments, but I think there might be some other magic going on with the IDs as well. So I think you can't rely on them to increment. So additionally, there's nothing stopping us from querying our database. And so we insert into our database, and then we can use .find1 to query. And in fact, we can query in many different ways. We can query, we can query the specific ID. And again, getting this inserted ID is the key there. We can query based on, the parameters of the objects inside of it. And so we can say name Eustis. And then we can even query off of things that may not necessarily be unique. And so page visits equals 0. And so what do we think each of these are going to return? Well, the first one we would hope is going to return my object in the database. And that would be correct. It does return my object. The second one also is going to return my object because there's only one person with the name Eustis. One difference between these two is that ID is by default indexed. And so that's going to be actually significantly faster than doing it with just my name. Now, of course, in our specific example, we have 2 items. So significantly faster probably is not necessarily true. In fact, it might actually technically be slower. But, when we get to 10, 100, 1,000, 10,000 items, it's going to be way faster. And then finally, we have page visits is 0. Well, we both have 0 page visits, so what's going to happen here? Maybe not such an exciting answer. It'll pretty much just get the first one. In this case, it's me. I think you probably can't rely on it being the first one. And so really, if you're if you're expecting to get everyone, or if you're trying to get a specific person with a query like this, just be a little bit careful, right? And we can see up here that we did in fact get me all 3 times. If you do want to get multiple people, there's nothing stopping you from doing that. Just instead of this find one function, hopefully unsurprisingly, we'll use a function called find. We'll pass in page visits is 0. Once again, we know both of us have that. And this will return something that we iterate over. So for document and found items, we'll print the name and we'll see Eustis Matt, right? Of course, each of these documents is kind of this full dictionary that we're being returned, but we're just kind of getting this name attribute right here. Wonderful. So Let's now look a little bit more generally at some of these collection methods that we've been using. And so we saw find. We saw find one. Now, one thing that I'm going to point out is some of the notation on these may be camel case, like you see here. This is the distinction between the Python API using PyMongo. We can see find underscore one and kind of the natural MongoDB functions. Of course, when you have MongoDB running on your own server, you can run MongoDB commands in its own shell, we'll say. And when we see things like this, that's what those represent. And generally speaking, I'm going to kind of try to stay a little bit closer to that side because you may be working with this in Python, you may be working with this in JavaScript, you may be working with this in the MongoDB shell itself. And so we want to stay a little bit more general here. But, generally speaking, all of these things are going to exist. So find obviously is going to return you kind of an iterator of all of the objects that it found. Find one is going to return you one, or I guess none if it doesn't exist. And then count will just tell you how many things it found in there, how many things it counted. We have some easy adding and removing ones, remove and insert. Let's take a peek at how insert maybe works. Oh, I think we do that in a bit. Or rather, we did that. Apologies. So we did insert one. Additionally, you can pass in, a list of dictionaries and it can insert multiple things at the same time. There's many, many more of these. We call them collection methods. Of course, we call them collection methods because they are methods that we call on a collections object. And I encourage you, maybe if you're going to be working with MongoDB, to look at some of them on the documentation. But these are kind of some of the basic ones that we'll just talk about. But let's look at maybe some more advanced queries we can do. Obviously, just being able to query a specific thing isn't maybe the most powerful. We want to kind of increase how many variables we can have. And so we can do things like this. And so what we can say is, I would like to find all of the documents where the page visits is less than one. Right? And so, we can see here kind of the format here is replacing that single variable with another dictionary with these variable parameters. Hopefully this LT should remind you a little bit of bash. And of course, as you may be able to imagine, there's many, many, many of these kind of keywords, less than. You can do and start to do Boolean logic. And so it wildly expands the capabilities of these queries here. And once again, we'll, just print all of them and we get the correct answer there, Eustis and Matt. But, we can even tie kind of these queries together with our edits. And so we can say, okay, I would like to update many rather than, update one. I'd like to find all of the documents where page visits is less than 0. I meant to make that equal to, my mistake. Had to change it back. Anywho, and then we'll set each of those, or rather we'll set a parameter for each of those, and we will set the page visits attribute to be 1. And so, in this specific case, this isn't going to do anything, but if I screenshotted when I ran this correctly, then this would have been less than 1, and it would have changed all of the documents that have 0 views, or I guess negative views, if that is a case, to have 1 view. So we've talked a little bit about graph databases, and in fact, we're going to go back to talking about object-oriented databases in a little bit. But I also want to kind of introduce you this idea of graphical databases, and the reason for this is not necessarily because graph databases are, I'll say, widely used. They're definitely a little bit more niche and a little bit more lesser known, lesser implemented, but they are super cool and they're super interesting. And as honor students taking an honors course, I think that it's very valuable to teach you things that are super interesting and super cool that you're not going to see in a lot of other cases. And so we'll look very briefly at graph databases. I'm not going to go into teaching you how to query in graph databases. They of course have their own language, which is I'll say SQL adjacent. And we're not going to go into maybe implementing it, but we will look at some examples that I think are kind of interesting and cool, and maybe we can talk a little bit about them. One moment. Okay. So graph databases are, again, as I mentioned, much newer. We're not going to go too deep into it. They're a really, really, really good choice for when you want to do analytics on a data set that is inherently, we'll say, graphical, of course. And what that means is it's made up of nodes and relationships between nodes. Um, Graph databases kind of have the ability to have very efficient queries and very efficient analysis of data that is laid out in such a way. Much more efficient than if you were to try to do it with other things. And so what we're going to do is just kind of look at some basic examples. And so we can use graph databases to try to do NBA playoff prediction. And so we'll have our schema here. We have year has this month, has this day, games occurred on a day, teams played in games. Games have the property of who won. These connections, a team, these connections are played in, the score, the differential, if they were away or home. And so, we can actually turn this into a full kind of organization of different events. And we can look at maybe an entire NBA playoff prediction and start to do, very interesting analysis on this. And so let's say two teams have never played and you want to try to figure out how they're going to do against each other. Well, we can find all of the shortest paths between those two teams and figure out who won more often against who. And so an easy way to think about this is if I won against a team who won against the team I'm about to play, it's likely that I'm better than that team. Excuse me. It's likely that I'm better than that team, right? But what if there's many other relationships, like I lost to a team that lost to someone that lost to someone that lost to them, right? Kind of going one step further. Again, graph databases are going to allow us to look at all of those relationships all at once in a very efficient way for huge data sets. And so I really do want to just I guess harp on the fact that with many things, many things can be laid out in a relationship that is graphical, and B, there's many powerful graph algorithms that we can then run on these data sets that are going to be super interesting. Similarly, we can visualize Wikipedia, and so all of these links are going to be the Mike Vernal page links the .NET framework. And so we can just kind of visualize all of the different pages that are linking to each other. Obviously, this is not all of the Wikipedia pages in the world, but maybe it is interesting. And in fact, we can do even more analysis on this. And so we can say, what's the shortest path from maybe Microsoft to Time Magazine? Well, maybe we'll go Microsoft, .NET Framework, .NET, Mike, Facebook, Apple, Time Magazine, right? And so, maybe there's some interesting stuff we can do here. I hope, some of you have heard of there's this Wikipedia game where you go to a random article and try to get to, some other specific article. Obviously, if you were a graph database, there'd be, or if you had a graph database, there would be a very easy way to do it. Yeah, wiki races. It's great. I love wiki races. Additionally, we can kind of do this with companies. And so there's this fun example that I found of visualizing the graph database companies, which is a little bit meta. But, we can have companies which, have different markets and different products, different services that they offer. They have different tags, so information about them. We have, I guess this is conferences that have that tag, graph query languages for that, information something that has that, right? Information sources, I believe. And then we can visualize it, and maybe we see that this one is a little bit more of a mess, right? A lot more going on. But just the ability to kind of visualize things in this way, and then to run algorithms on this that can easily say, okay, this person is kind of at the heart of all of the graph database companies, is something that could I guess, we're not really business majors, but it could inform business majors' decisions to try to, strike a deal with someone who's very important, right? I can't point out any specific companies very easily. Maybe this company right here. I think this is a company. Which one's purple? Oh, it's a different color scheme. That's fun. Anyway, we'll pretend that this is a company here. If I'm over here and I'm trying to get into this market here, making a deal with this company is probably going to be very important, right? Apologies for the slight interruptions. Additionally, and this is a very exciting one for me, is we can visualize UIUC classes this way, right? Obviously, the relationships between them is that there are prerequisites, postrequisites, co-requisites. I actually attempted to do a project in this at one point. This is not my project. This is someone else's under Wade. Wade obviously is a professor here that makes some awesome visualizations. Hopefully you have used one, the GPA by section or GPA by course. It's very useful. But we can actually kind of explore this live, and we can see these different visualizations. And so I think one of these is, yeah, there's CS125. We're not listed on here, unfortunately. I think this was a little bit before our time. CS173, which then links to CS225 right here. Yep, CS225, which obviously is then going to branch out to many, many other things. And you can actually get pretty interesting analysis from this. And so we can say, okay, what's the longest sequence? Well, 125, 173, 225, 233, 241, 2426, 526. It's hard to say that many numbers fast, but of course, we're not even restricted to doing this in CS. We can do this for, I guess, theater classes. We can do this for liberal arts classes. We can do this for languages. The what is that, 9 Spanish classes in a row. We can do little, analyses like this with linking prerequisites together. And so we can see, many math classes or many ECE classes have math prerequisites. Many civil engineering. I can't remember what CE is. Have many TAM prerequisites. Then, even look at the longest class chain in all of UIUC, which goes from algebra to excavation in support systems. So many, many interesting things you can do here. Classes are a little bit of a difficult one because there's data is kind of hard to structure with co-requisites, prerequisites, all of those things, as well as classes that are cross-listed. It can become pretty hard. So big respect for whoever made this. And of course, we've been discussing some of these algorithms, but we haven't actually been, naming them. And so we'll name a couple. There's kind of 3 major categories of graph database algorithms, which is centrality, community detection, and graph similarity or node similarity. Centrality, of course, determines how kind of central a node is in a graph. One of the major is even harder to scrape course info. I know, I have done it. It is very not fun. One of the major categories or one of the major algorithms for centrality is Pagerank, which was made by Google, and it lists Google searches. Of course, someone then built on this, and many, I think hundreds of people have built on this. But one kind of interesting one that I like to bring up is Twitter Rank, which is just the Pagerank algorithm applied to Twitter followers and Twitter followings. That's used to see who has kind of the most influence on Twitter. I can't remember who it is right now. I remember years and years ago it was the president, unsurprisingly. Or maybe it was some celebrity. I can't remember off the top of my head. Headphones stay on. There's also community detection, and there's different algorithms for these. Louvain, I hope I'm saying that right. Label propagation, triangle count. You again don't need to know all of these in specifics, but hopefully if you run across any of these in the wild, you can say, oh, that's a community detection algorithm. And of course, all of these kind of algorithms are going to tie pretty closely into the math side of things with graph theory. But that's definitely not the topic of this course. But if any of you are interested kind of that content, some of these may be interesting to you to work with, or even graph databases may be interesting for you to work with. But community detection, as the name may imply, are used to detect clusters in a graph, which can then be used for all sorts of analysis. And so, for this here, we can see actually some cluster detection going on with the coloring of different groups. For this one here, we could see, clear applications of clustering with, I guess, topics. And so it looks like all of these are kind of with graph analytics. It looks like all of these are for infrastructure. I think that says. I can't tell for sure. These are actually books about it, it seems. Obviously, I think with Wikipedia, graph clustering would be kind of interesting. And then finally, we have kind of the category of graph similarity algorithms: node similarity, k-nearest neighbors, cosine similarity. These again all give you information about how similar two, or two groups of nodes are. These have tons of applications in graph theory. I think one interesting one that it can tie pretty closely into is like the whole map problem. Like, can you color any map with only 4 colors? I'm pretty sure graph similarity has some pretty large influence in that field, or in that topic. In any case, let's look at actually tying a database into the example that we've been working with, right? So if we think back, in front end, we developed this very awesome framework, this wireframe. We turned it into actual code. In backend, we then kind of learned to serve that automatically and actually serve it on a server and host it on a server, and then to apply templating to it. And now we're going to be looking on how to kind of tie a database into it too. Now, unfortunately, I will spoil the party. I lost the file. I can no longer find the very beautiful web page that we made. And so instead, we'll just have to pass the parameters that we were passing to it to a random web page. And I know you're very sad and very disappointed, but yeah, I have no excuses. I think I deleted it by accident when I was cleaning out some files, so apologies there. If you want to make a new one, I'll use it for lecture next semester. So in either case, let's start to discuss this. So recall, in the past we were web scraping the CS196 web page for users, and we would kind of automatically display that on the web page. Of course, it's probably pretty inefficient to either web scrape the CS196 web page every single time, and it's also maybe not a great idea to web scrape it every time our server starts, or anytime any of our servers start, we should say, because many servers could be hosting the same web page. And also, it's probably not a great idea to just download the file like I did and scrape it each time we need it, because what if the web page changes? What if we added a staff member? Maybe many of you may become staff next semester if you're interested. If we want to add you as staff, we would need to kind of go through this whole process of re-downloading this web page and re-uploading it. We want to do that automatically, or rather have a database to kind of store that information, and so we can do it once and forget about it, right? And actually once and forget about it, I should say. So first, we'll do this in SQL. Python has a built-in Python module called SQLite, which is a implementation of a SQL database for free, basically, and so you actually don't need to worry about hosting a separate server. The downfall of this is that technically it's not a different server that's running. It just uses I think some sort of database file that I can't remember the name of. What's the extension? I can't remember. But it just stores it all in some file. Interestingly enough, SQLite 3 is what we used on the back end of your homework recently. So if you remember, you were interacting with a database. All of that was done using SQLite 3 and SQL queries on our end for testing. Fun fact. So we'll import, SQLite 3, nothing too crazy there. We'll get this thing called a cursor and a connection. So connection, hopefully shouldn't be too surprising. We're connecting to the database server. A cursor is the thing that we're going to use to interact with the server. I'm not going to get too far into the weeds on what a cursor is, but just know it is kind of an information about our connection. So of course, step one with creating a database is to create database, and we'll just call it website. Next, we'll create our table, and for our table we need a name and a path. I chose 50 and 200 characters. Again, sort of arbitrarily. It doesn't really matter. Path might technically be too short. I didn't really check with a lot. I'm pretty sure all of the URLs are less than 200 characters though, so I think we are good there. It didn't break in testing at least, so I think we were fine. In either case, I actually believe that we're only storing the last kind of substring of the characters as well. So this really probably only needs to be like 20. In any case, and then, when we're actually, if we remember, we had that kind of web scrape function that, got all of the names and URLs and turned it into a dictionary. What we'll do is, instead of returning that every time, we'll just run this once, which is, iterate over it for name and URL in the dictionary.items. Execute, insert into this table, name, URL. And so we'll run this, and it'll populate our database, and it works completely functionally. We'll load the web pages. We can actually load it right now. It's not localhost 4000. What is it? It's 5000. So we'll just go to like /Eustis again. The web page is gone, so it's very sad and boring. But we can see, Eustis in my profile picture there. We can go to Matt. Doing it live. Why did this just break? I'm so sad. It worked with me and then it broke with Matt. Still works with me. Did I like typo Matt? I put a space. Anyway, it works with me, and that's what's important, right? that is what's important. I apologize for the crash there. Yeah, I handle capitalization, so that shouldn't be the problem. In either case, it was working beforehand, so maybe you'll just have to take my word for it. Maybe I can troubleshoot afterwards and let you all know what was wrong. But in either case, that's maybe not as important. We'll just connect to the MongoDB client, and we'll see how this is done with not a relational database. Yeah, I promise. How about that? Not a relational database, but a object-oriented database, and how that's going to kind of treat us differently. And so again, step one, connect to the client, create a database, create a collection, and then we'll add to the database in this, very similar way. For name URL in the dictionary, we will insert into people, name URL. In this situation, what we're doing instead is collection.insert1 name URL. Now, is there a function that I could call in this situation that would insert all of these things at once? Definitely, right? This is essentially a big long dictionary of names and items, and so I'm certain that we could do this all at once. But I didn't, so instead we're doing it this way. And the next thing that we'll do is on the GET request, we search the database here. And so we say item equals collection.find1 name, right? Again, we're searching the collection for a single item that has the name. And then we will retrieve the URL itself. And so that's all the way over here. Again, this item is going to be that entire return kind of dictionary. And then we will just get the URL for that. I'm trying to think if this is where, this is definitely where my bug is. I'm trying to think how to easily fix it. I should not be doing this right now. Oh, I see the problem. Okay, so just in case you all are interested in knowing what the bug was, way back here, when I added Matt and I as users here, I actually never cleared Matt and I from the database. Actually, I cleared me, but not Matt. And so when we get Matt, when we run this line here, this collection find name, well, it's searching Matt, and the first Matt that appeared is the Matt that does not have the URL attribute. And so this is a great maybe example, doing it live example of why you should probably have all of the same schemas in a specific collection. In my case, I didn't, and now we have run into an error that was completely unplanned, let it be known. So instead, we'll look at Tim, because Tim was not put into the database before, and it's Timothy. And so there's Tim, my good friend, who goes by Tim, not Timothy. We should fix that on the web page. Headphones, stay on. So next, my headphones just turned off right after the noise played. Okay. In any case, now we'll just cover kind of some miscellaneous topics on designing good databases. This is a topic that I think is maybe not necessarily necessary, but if you are all designing databases, it's I think good to know. And so we'll be going over to these things called normal forms, which is just a way of laying out relational tables so that things don't break, essentially. There's tons of these. I think there's like 6, and then there's like 4 more or something. We're just going to be going over 3, which are the 3 base ones, which I think are the easiest to understand and also kind of the most important, the most common mistakes. And so the first one is pretty simple. Columns must be atomic, which means they are either a single value or they are null. Basically, this means don't have tuples inside of your columns. Don't have multiple things inside of your columns. They are either, the state that that certain thing says they are and only that, or they are null, meaning, they're kind of nothing. So this one's pretty simple, right? Don't have tuples in your columns. The second normal form, it says, have the first normal form, and also try to avoid this thing called partial dependency. And what partial dependency is all of the other columns depend only on part of your primary key. And so let's break this down. Is first, part of the primary key. What does that mean? Well, in this situation here, we have student ID, which is not necessarily unique, right? We can have multiple, or we can have one student on multiple projects, but the combination of student and project is unique. And so that becomes our primary key, both the student and the project. But student name depends only on student, and project name depends only on project number. And so we have this thing called partial dependency, meaning Katie, the student name, depends only on part of the primary key, and project name depends only on the other part of the primary key. So this is very bad practice, and we'll see a great example on why this is bad practice when we actually look at the third normal form, which we'll see in just a second. So how do we fix this? Well, just turn it into two separate tables, essentially, right? The first one, student ID, project number, student name. Of course, project number depends on student ID, student name depends on student ID, so we're good there. Or rather, we still have the primary key being here, which is my mistake. But this is good. And then project number, we're splitting this geo location stuff, the project name, into a separate table, and so we're good there. Now the third normal form is this thing called no transitive dependency. And so transitive dependency is maybe what it sounds like, which is one thing depends on another, right? And so in this situation, we have author. Author is directly dependent on title, so we're good. Author nationality, however, is dependent on author, which is then dependent on title. And so the question I have for you all is, if we remove all of the books by that author, maybe we're not selling books by Chad Russell anymore, we are also going to lose what nationality Chad Russell is, right? And in fact, you lose all of the other things that are maybe transitive to this author property. And so you really do want to avoid that, because we've suddenly, lost information that maybe we didn't want to lose. And if we tried to add a book by Chad Russell back in the future, and we tried to look up in our database what nationality they were, well, we wouldn't be able to, because we wouldn't know. It wouldn't be anywhere. And so my question to you in the quiz that we'll do is, and this is basically the end of lecture, is where else does this occur in our example? Let me make okay, so pollbot should be up. So go ahead and react to that. With what other column do we have transitive dependence? So again, author nationality has transitive dependence because it is dependent on author, which is dependent on title. Technically speaking, author nationality is dependent on title, but it has, more importantly, that transitive dependence through author. Chad Russell got deleted outright. Exactly. So there's one other column that this happens, right, where we have transitive dependence. And so I'll give you all just a moment here to try to figure that out. Okay, so let's maybe start to review it a little bit, and I'll close the poll kind of halfway through this. Okay, so, let's kind of go by these one by one. Well, pages. Okay, is pages dependent on anything? Publisher ID, no. Genre name, no. ID, no. Thickness, probably not. Author nationality, no. Author, no. Title, yes. So, that is not the case. does thickness depend on anything? No, not really, right? Again, like maybe with pages, I'm not sure if thickness determines if it's a thick book or if it's paperback or hardcover or whatever. But in either case, it probably just depends to the title here. Genre name. Well, genre name depends on, or rather, does genre name depend on title? Can we determine genre name based on the title? Maybe. Does it also depend on genre ID? Yes. If we remove all of the titles, are we going to lose the, or rather, if we remove all of the things of a certain genre ID, are we going to lose what the genre name for genre ID is? Yes, we will. And so I'll close the poll right then. Row. Okay, there we go. Thought my internet went down for a second. That was scary. And so, yeah, we can see a little bit split responses here, but the majority of people did put 3 genre name because, again, the important thing here is if we remove all of the essentially genre ID ones, we then lose the genre name that was coordinated with it, that was transitively dependent on it. And then finally with publisher ID, right? There's nothing that has that case. And again, another way if you want to just think about this is, is something that it's dependent on. If all of those things get removed, do we then lose that information, right? Maybe that's an easier way to think about this. Now, I had some extra time for a live example, but there's 2 minutes left, and so there's probably not enough time for a live example, unfortunately. I think what we'll do is maybe just look a little bit at kind of this MongoDB Atlas, and just see some of the stuff that it has. Though I'm not frankly sure it's very exciting. So obviously these online databases are going to give you a ton of kind of troubleshooting stuff for how many queries are happening and whatnot. Of course, there's alternatives to this. I think I use Firebase for a project for my website. And so we'll take a peek at this. Yeah, here we are. And so, this is just like MongoDB Atlas. It's a database that's being stored. Interestingly enough, when people go to my website, I store their mouse movements, which is a little bit Big Brother. But the idea is that I'm going to eventually train a model to move the mouse like they would move the mouse, or rather move fake mouses like they would move their mouse and try to predict it. Additionally, I just store stuff like how many views my website has. Nothing too exciting right now. But could I do this in a relational table? Maybe it'd be pretty tough because these can be super long and also super short. So that could be a little bit tough. But again, these are all just kind of database hosting services, and they give you the information on how to connect to them. And so it really is amazingly easy. I mean, to set up MongoDB Atlas took me 15 minutes probably. And I had never used Atlas before in the past. I had hosted it locally. Okay, in either case, that basically brings us to the end of lecture here. It's about 7:50, so I hope you all kind of enjoyed this section on web dev. All of these web dev lectures were new to this semester, and so we'll probably ask for some feedback, maybe in the near future, more likely near the end of the course. And so, if you do have any feedback on if you liked it or not, shoot us a message, shoot us what you liked and what you didn't like. If you want it to be anonymous, maybe wait a little bit towards the end of the semester. Maybe you'll forget about the anonymous, critiques that you have. I'm kidding. Please give us all of your critiques, albeit hopefully constructive. But yeah, thank you all for kind of coming to these lectures. The next topics that we'll be covering is kind of, again, some miscellaneous stuff about how to get an internship, which is a favorite by far. Tons of people love that lecture. And then I'll talk about machine learning, which hopefully will be a favorite. And then we'll be getting into our Rust section, which will cap out the course. In the not too distant future, I do want to remind everyone that we have midterm presentations. So your group will make a short presentation on your progress thus far and kind of receive feedback and ideas on where to go. And so be a little bit prepared for that in the near future. Ask your PM about it. But thank you all, and I will see you, well, rather Matt will see you on Tuesday. Bye-bye.